as I was saying right when the camera cut off, the only thing that I really have to switch, the free body diagrams themselves are great. They are fine. But one of the things we just talked about was that the tension is not the same throughout the string. So what I'm going to do is I'm going to talk, instead of just tension, we're going to talk about the tension of the part of the string near the 2M side, and we're going to talk about the tension on the part of the string near the side that just has the mass of just M. So here's what I'm choosing to do. I'm going to go back to my free body diagram, and I'm going to label our equations a little bit differently. And actually, I'll just write them over here. Okay? So now it's the same diagram. I'm not going to write the diagram over again, but we now have F net x equals T, we'll call it T2, equals M2 AX. We know this is T2 equals 2M AX. I'm not even going to bother rewriting this one. This one doesn't change at all because of the tension. And over here, so this is for 2M. And then for the mass of M, we have F net x equals F1G minus, I'm just going to call it T1, M1 AX. We know this is M1G minus T1 equals M1 AX, or in other words, just MG minus T1 equals M AX. Now, that takes care of the forces, but since I'm dealing with a pulley that rotates, I need to take into account the rotational inertia of the pulley. It means I need to talk about the torques that are acting on this pulley. I need a free body diagram for the pulley itself. Here's the pulley. Okay? There's our pulley. Here are the forces that act on the pulley. Obviously it's hinged like right here, not hinged, but it's set up there. It's kind of, let's say that it's mounted on some sort of axle. Okay? So I guess you could say that there's some sort of normal force going up like this. You could say that since the pulley has mass, there is a force of gravity acting down, FGP, we'll call it. And for this pulley, most important thing is that we now have two forces causing it to rotate, generating torques. We have T1 and we have T2. We need to do a net torque equation for this. Now, if you remember, I have two forces, that are acting at the axis of rotation. They don't cause any torque. The normal force does not cause a torque. The force of gravity for this pulley does not cause a torque. Torque is only caused by T2 and T1. So when I go to write the net torque equation, okay, oh, there is something that we have to be careful of here. I remember what it is. Okay, so here's the thing you have to remember. We said that, it kind of has to deal with this. If we said that 2M moving to the right was positive x and M moving down was positive x, which way would the pulley be forced to rotate if that's the case? If 2M moves to the right, M moves down. It would move clockwise, right? Well, so that we don't screw up all the signs, therefore we have to say that clockwise is positive here, because it aligns with, this is moving to the right, we consider that positive. This is moving down, we consider that positive. That motion causes the pulley to rotate clockwise. We have to call that positive. So when we come up with the net torque equation, the clockwise torque is T1. So I'm going to call that torque 1. This is actually the counterclockwise torque, and I know counterclockwise is typically the positive one. Guess what? It's not here based on some conventions we already set. So I have T1 minus T2, and that is always equal to I alpha. Now I'm going to make some substitutions here. Okay? I'm going to make some substitutions with this net torque equation. I know the equation for torque is R1 F1 sine theta 1 minus, might run out of room here, R2 F2 sine theta 2 equals I omega. Here's the axis of rotation. here is R. In both cases, R is perpendicular to the force being applied, the tensions from the strain. Therefore, we can say that these are both 1. And up here, we said that the radius is R. We can just write that these are both R. So what I have right now is T net, torque, the net torque, equals R T1 minus R T2 equals the moment of inertia multiplied by the angular acceleration. Moment of inertia for a pulley, for a disc, okay, that rotates is 1/2 mr squared. 1/2 m, and this is the mass of the, what is this, what did I call it? The mass of the pulley. I'm wondering if I should have changed something there. Okay. I know what I said. We're essentially saying that this mass, the mass of the pulley, the spinning disc itself, is the same as this mass. Okay? Not always going to be the case. Sometimes you have like this is big M, these are both big M's, and this is a little m. I set this problem up so that the pulley has the same mass as this. Okay, that's how the problem was set up. So, mass M, R squared, 1/2 mr squared, that's I, and then, do we want to do anything? No, we'll just, you know what, we'll leave this as alpha for right now. So what I have here is I have 3 equations, and essentially what I have are, if you look at it right now, it looks like I have 4 unknowns. I don't know T2, I don't know T1, I don't know the angular acceleration, sorry, that's that one, and I don't know the linear acceleration. Turns out that I can take one of these, and there is one variable that I can get rid of right now. But what I want to do first, what we're going to solve for first, is the linear acceleration AX. And it's going to look kind of weird how I'm going to do that, is I'm going to take this equation to start off. So I've got this is the part where I've got my net forces, I've got my net torques. Everything after this step is just algebra, and like one substitution. So I'm going to take this. It's, like I said, it's going to get messy. I'm going to bring this over, I'm just going to write out R, wait a sec, I could probably solve this for T1, right? If I add this to the other side and I bring this, so I add the T1 to the other side and I bring the MAX over, then I'll have this. I would have, let's see, I would have mg minus max equals T1. Of course my computer is going dark because I haven't moved it in so long. And I can bring that in to this equation. R mg minus max. And now I've replaced T1. So that's the RT1 part. RT2, well I have T2 right here, minus R2max equals 1/2 m r squared. And you know what? Alpha I can substitute for, because it turns out that alpha, there is a way to but to equate the angular acceleration and the linear acceleration. Maybe you remember this little equation, where we had, what was it? A equals R alpha. Very similar to V equals R omega, or S equals R theta. If I solve this for alpha, I get the linear acceleration divided by the radius is equal to the angular acceleration. Very, very important. I'm going to plug that in. A over R. And now watch what happens. Okay? This A, this is a linear acceleration. This is basically saying what's the acceleration of like a little point on this disc, okay? On this disc that's rotating. Well, the acceleration of a little tiny point, the linear acceleration of a point on this disc, has to be the same as the linear acceleration here and here for those masses, okay? Wouldn't make sense if this little point accelerates more, okay? It increases its linear velocity more than these increase their linear velocity. This is actually AX down here. So what I've done is now I have, let's see, well, everything's in terms of AX. Great. But there's more. Look right here. I right now have 1/2 mr squared times AX over R. I can get rid of one of those R's. I cancel out this squared, I cancel out this. Great, now we don't have fractions anymore. But now look what happens. Look what I have in every single term. This term has an r, this term has an r, this term has an r. Guess what? The r's all go away. What else is in every single term? M, 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 M. Look at all that cancellation. Cancel, 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 and so on and so forth. What am I left with? G. If you want, I would probably rewind this just to see that again. Okay, I would probably take a look until you understand why I'm canceling everything out, why everything can cancel. Do the math yourself if you need to. G minus AX minus 2AX equals 1/2 AX. We're solving for AX here, so I need to get all the AX terms on the other side. So this side, I'm just left with G equals, let's see, this would be minus 3AX, I add to the other side, so that's plus 3. And I have 3AX plus 1/2 AX, so that's 3 plus 1/2 is 3.5. I don't like that though. Instead of saying 3.5, I could say 7/2. You guys are probably like, you idiot, why would you say that? Well, make your lives miserable. If I'm solving for AX, I multiply, or I guess I divide the 7/2 over, or I multiply by 2/7. Here's what I'm left with. 2/7 times G equals the linear acceleration AX. Let's compare this, okay? 2/7. We now have an angular acceleration, or no, I'm sorry, a linear acceleration, taking into account that this is something, there is rotational inertia, okay? It takes a little bit more to make this rotate. Well, we didn't change any of the forces here. So instead of taking more for it to make it rotate, it's not going to speed up as much. The linear acceleration is going to be less. 1/3 times G is greater than 2/7 times G, okay? Because 2/6 times G would be the same as this. This is a smaller number. So it turns out that when we factored in the pulley, the rotational inertia of the pulley, it's not, the system will not accelerate as quickly. That makes sense. We're taking into account some extra mass that we didn't take into account before. Therefore, the system just won't accelerate as much. It would be like if we had some undiscovered mass like over here. Oh, it's not going to accelerate as much. Instead of just undiscovered mass here, we're taking into account the pulley. There's not going to be as much acceleration, okay? That's very, very important. We've got AX. Now we can find some other things. We know that the angular acceleration is equal to A, the linear acceleration, over R. So I could do this. I could say alpha equals A over R. Alpha equals 2/7 times G over R. Alpha ends up being, how did I write this? I'm sorry. 2 over G, or 2 times G over 7 times R. Okay? Now, that's kind of a standalone. We didn't have an equivalent to that in the other one. But that is very important. Alpha equals 2G over 7R. Okay? The angular acceleration. We got that from this right here. This is important. The last two things we want to find are the tensions. Before we said the tensions were each equal to 2/3 mg. We said it was the same tension throughout. That is not the case anymore. There's my trick. Finding tensions is pretty easy. I know that T2 is 2 times m times AX. 2m, AX was 2/7 times G. The T2 up here is now, let's see, 4/7 mg. And T1, I should separate these. Let's see, we had mg minus T1 equals m AX. So we had T1 equals mg minus m AX. AX is 2/7 G. So let's see, they both have mg in them. This is 2/7 times mg. This is, I guess you could say 1 mg. Or you could say 7 over 7 mg. I guess I'll write that over here. 7 over 7 mg minus 2/7 mg. T1 is 5/7 mg. Compare this to the original tension. We got two different tensions, 4/7 mg and 5/7 mg. Which one is bigger? Kind of makes sense. This tension has to be bigger because it has to make the pulley rotate clockwise. If this was bigger, then that would mean that the pulley rotated counterclockwise. Wouldn't make any sense. This tension is slightly bigger than this. This tension is slightly less than this. So there are very minute changes. If you were to do this in real life, when you have a pulley of mass m and two boxes of 2m and m hanging like this, this would give you pretty good results. Factoring in the rotational inertia of the pulley would give you a little bit better results. Okay? If this pulley has mass, you have to take it into account. Now, 80% of the time, that won't be the case. But in the case where you have to take the mass of the pulley into account, you need to do a net torque analysis, which you've done before. Okay? We did that all the week before you guys left for break. Now we're just putting it into a different type of problem. We're plugging it in to somewhere new. Okay? We're integrating everything. I think